Hello, and thank you for joining us for today's webinar. During this educational webinar, we are going to be discussing 6 different types of root causes of premature pavement failures and how to identify them and ways to avoid running into these with your pavements. A little bit about Benchmark. Benchmark Inc. is a professional roof and pavement consulting firm. We provide companies across North America with objective and technically sound consulting services that include evaluation, design, construction phase services, and program management, all to reduce risk, prioritize budgets, and maximize the service life of your roof and pavement assets.
So your presenters today are Troy Kaiser. Troy is our lead presenter. He is a senior consultant with Benchmark Inc. He's been with Benchmark since 2006 and has over 35 years of experience in the pavement industry. Troy enjoys finding just the right solutions to his clients' problems, and he is passionate about cultivating relationships with his clients. I will be assisting Troy today, and I am Elise Schmidt, General Manager of Benchmark's Pavement Division. I've been with Benchmark for 16 years and have the pleasure of working side by side with Troy each and every day. So with that, I'm going to hand it over to Troy so that he can run through the 6 premature pavement failures.
Thanks, Elise. We're actually going to use some actual projects that we've worked on, and I'm hoping to be able to point out to our viewers that the only way to really fix a pavement problem is to find the root cause. Starting with what a premature pavement failure is, it's any failure of a pavement that occurs before our design life. If you look at the pavement on the left here, it's a concrete pavement, and we expect concrete pavements to last 20 plus years, but as you can see, this 5-year-old concrete pavement has already failed, and it's already actually been patched, and the patch is failing. So definitely a premature failure. Slide on the right is a condominium project that we were brought into. This is an asphalt roadway that was only 2 years old, and you can see it has a pretty significant isolated area of failure. So as we move forward here, we're going to look at some different case scenarios. We're going to look at the 6 root causes that we feel cause premature pavement failures. They are poor soils, drainage, traffic usage, improper materials, improper design, and lastly, not following the design or lack of construction oversight and quality assurance. Okay, number 1, poor soils. Any pavement you build, whether it be asphalt or concrete, are only as good as the foundation that you put them on. So you have to have a really strong foundation. The project on the left here, this is an 8-foot wide asphalt. It's actually a pedestrian walkway at a pretty high-end shopping mall. And you can see the failures in it. It's starting to rut, where the tires run from what I assume are landscaping vehicles or snow plowing vehicles. The asphalt's pushing down where the tires are, and it's pushing up in between the tires and along the edges, kind of what I call a farm road kind of profile that you see with gravel farm roads. Obviously, premature failure. This was only about 2 years old when we visited this site. And then this rutting is a good indication of poor soils, that the base is soft. What's underneath the pavement system is not a good foundation. On the right, we see a concrete pavement, and what cued me on this project when you're brought in, you can see the concrete slabs are not just cracked, but they're faulting and rocking, showing that there's no support underneath. So these are 2 examples of poor soil.
So Troy, quick question. With the concrete picture here, do we have any idea what the age of that concrete is at the time of the photo?
That concrete pavement was approximately 5 years old. So it was, for concrete pavement, it was a very young pavement to have this kind of failure.
Wow.
And I'd like to point out, at least on the asphalt pavement, you can see the roller marks. So this was soft from day one when they paved it. You can see the lines running the same direction as the path. Those are marks that were left by the roller. And if there isn't a firm foundation underneath the asphalt, you can't get compaction and you can't get those roller marks out when they're doing the finish rolling. Now, what is a poor soil? Well, we have several types of soils. There's sands and gravels, which are what we classify as good soils. Clays are good soils, but can be potentially affected by moisture. And here we have two examples. The roadway on the left, the asphalt and the stone base has been removed from this roadway that's being reconstructed. What you can't see is that the old asphalt was very cracked and was allowing a lot of water to infiltrate down into the soil. And as you can see from the excavation trucks, the soil is moving and rutting because it had all of that moisture that had gotten into it. In this particular case, we were able to dry that soil out, recompact it. It was very hard once it had dried in the sun, some wind on it, and we were able to put a new stone base and a new asphalt pavement on here. The other thing that can happen to soils when they get wet is they can expand, or what we call expansive clays. There's an example of this on the right. The soil underneath this pavement got wet, expanded, and it pushed the asphalt up. And it can also cause very wide cracking. Wide cracking up to 8-10 inches wide is a good indicator of a failure caused by expansive clays. Soils that we should never build on are topsoils or organic soils, peat. They're never stable, even when dry. So before we build any pavement system, we want to make sure that there's no topsoil or peat layers, that they're removed before we build our pavement system. I included this photograph to show that a poor foundation or a poor soil that ruts like this during construction, you'll never be able to build a quality pavement over the top of this type of soil. The next root defect we're going to look at, or root cause, is drainage. These are two examples of surface drainage or poor surface drainage that will cause premature defects. We'll start with the photograph on the right. As you can see, there's a flat spot around this island at the shopping mall, and it's ponding water. That water sitting on that pavement is going to cause that pavement to deteriorate quickly. Water will soak through a pavement even if it doesn't have cracks. It'll soak down in, soften up what's underneath. The pavement will then crack because it'll move, and then the cracks will allow more water in, and the deteriorated area will grow larger than what this ponding area is. So when we see a failed area, we need to look for signs of surface drainage issues like staining, silt that's washed into the area and then doesn't wash away. That'll give us a good indication that that failure was caused by poor drainage. The slide on the right is a shopping mall that we were called in on, and they water their islands and irrigate their islands every day, causing excess water to flow away from the island. This water flowing across the top of the pavement like this every day is going to cause that pavement to deteriorate and fail. It's very similar to downspouts on a building. A lot of water comes out of roof downspouts and will cause deterioration of concrete and asphalt. And you've got the same thing going on here. And if you look at the slide carefully, there's actually a crack that's running parallel to how the water's draining. And I'm sure when the water's coming out heavier, it's getting in that crack, and that surface drainage is going to cause deterioration. So we need to water these islands a little bit less, or get some kind of under drain system underneath there to take the water away from the pavement so that it's not going across the surface every day. The other aspect of drainage that's important to look for when trying to diagnose a premature failure is subsurface water. Water underneath the pavement, whether from springs, sometimes even leaks in water lines, will get into the sub-base stone, the sub-base soils, and cause softness. And with a soft base, our pavement will fail. The slide on the left, this is an area that we excavated. This is a ring road on a shopping mall area. When everything was removed, it was this wet. This isn't after a rainfall. This is how wet it was underneath this pavement. And I'll get into this a little bit later, how this was resolved, but that was what was causing this pavement to fail, was all this moisture underneath. If you look to the right, this road, this is actually a project we're working on right now, had been repaved once. They were trying to figure out why it was continuing to fail. Well, If you look beyond the pavement here, you can see water is sitting on the edge. There's not a real good ditch there. So poor drainage along the side of that roadway is allowing that water to soak underneath the pavement, soften up the base and the subbase, subgrade. And then as traffic goes over it, it cracks the pavement, allowing more water to go in. This is pretty obvious here because it had just rained, so there is water actually sitting in a rut in the roadway. But even if this was dry and there wasn't any water on the surface, you could look to the shoulder and say, this is probably a failure due to poor drainage. How we're solving this issue is we're going to put a new ditchway along the side of this road to carry the water away from the pavement section. So always have to be looking outside the pavement failure for clues to what's causing it. Like I mentioned, once water infiltrates a pavement, it causes failure. And here's a couple projects that we're involved in. On the left side, we have a really good asphalt pavement. It's probably only 5 years old, but all the deterioration is occurring right along the edge. What we found is happening here is the water is running across the parking lot and dumping into the landscape area. And then the water sweeping back underneath the pavement into the crushed stone, which is more porous than the dirt in the landscape island, softening up that edge. And then, of course, the cars parked right up on the edge of that pavement, causing this damage. So this premature failure was caused directly by poor drainage along the edge of the pavement. So that would have to be taken care of before any patching or reconstruction would be done. On the right side, this is a concrete truck area in a plant down in Texas that we did. And we had concrete failures. And the concrete failures we found were not caused by a poor base. It had a sandy base, but none of the joints in the concrete were sealed. So water was getting in the joints, flowing under the pavement, washing away the sand. That was creating a void, air void under the concrete that the concrete couldn't bridge. So when a truck went over it, it would collapse. And you can see in the foreground that where the failure is, the concrete is actually pushed down. What made this even worse was the concrete had a very light reinforcing mesh when it should have had a heavy duty rebar in it. And most of the mesh was laid in the bottom of the construction area. So it was at the bottom of the concrete and not in the middle of the concrete where it should have been. So the concrete failed prematurely and couldn't bridge these gaps. So we ended up reconstructing this area with a new concrete with proper rebar, and we made sure we sealed the joints to keep water from getting underneath and washing away the subbase. Third cause of premature failure we're going to look at is traffic usage. We design parking lots for the type of traffic that we are told they're going to have or anticipate they're going to have. Unfortunately, we see things that happen like on the left here. I shot this photograph at a shopping mall. I was on the inner ring road where the garbage dumpsters are, and I noticed that he was dropping an empty dumpster right in the middle of the car parking lot, which is not designed for heavy trucks. But what made it worse was then he drove over to the dumpster, picked up the dumpster area, picked up the heavy dumpster, put it out in the parking lot, then picked up the empty one and swapped it in, and then went back out and picked up the heavy dumpsters. So using these pavements for things other than they were designed for will cause premature failure. The photograph on the right is another project we brought in on. This parking lot was used as a staging area for construction, a construction project at the mall or at the store. They had shipping containers parked here, and we're running forklifts between the shipping containers to the store to shuttle materials. And you can see that the shipping containers have damaged the asphalt here, and the forklifts running on it have caused damage too. So we need to know what traffic usage is on these lots, and that the wrong traffic usage is going to cause premature damage. Two more examples of how traffic usage can cause premature failures. The photograph on the left shows a outer ring road at a mall. This pavement was reconstructed 6 years ago using the same design that was used on the other side of the mall for the ring road, which was working okay for the owner. So he went ahead and reconstructed this side of the ring road, the mall ring road. But what they didn't take into account here, and the paving contractor didn't catch this, was you can see there's a bus drop-off area here where the city buses come and drop off people to go to the mall. Well, this bus traffic is very heavy, really hard on pavements. And so here the traffic usage didn't match the design thickness of the pavement, and it totally failed within 5 years. The photograph on the right is another example of traffic usage. This is a parking lot that a customer of ours turned into a truck trailer parking area with no dolly pads. This parking lot was obviously designed for cars, but now with the trucks on there and the trailers being parked on there, you can see that it's failing way ahead of when it should have. Concrete usage for traffic. The photograph on the left was a project we had where the project was built when we had shorter semi-trailers, and then the longer trailers came out, and now the landing gear don't sit on the concrete, causing failure of the asphalt pavement. What we did here is we extended the concrete out, and so that the dolly pads now sit on concrete, because obviously filling in the divots with asphalt like they did in the background did not work. And then on the right side here, anytime you have these small forklifts with the hard rubber tires, they're going to cause premature failures. So as you can see, the pavement here, that's actually a concrete pavement, but must not be very thick, failed where these forklifts are running in and out, and they actually had to spread stone over the top of it to fill in the holes so that the forklifts wouldn't get stuck. So traffic is another big factor in premature pavement failure. Next root cause would be improper materials. We want a good foundation with good soils, but then we want to use proper materials. Either our crushed aggregate base, our concrete, our asphalt need to be properly specified for the project. Crushed aggregates, everybody thinks rock is rock, but crushed aggregates can be crushed limestone, crushed gravel, harder rock, crushed asphalt, crushed concrete. And what we found is that if you specify materials that are crushed and have angular faces, they lock together better. You put fines in there to fill in the gaps. And if you water and compact these materials when you install them, they get very hard and they make a good base. Fortunately, a lot of areas of the country will use rounded gravels with rounded stone, and those rounded stones act like ball bearings and make that material unstable for paving on. And worse for asphalt paving, because we have to run our trucks over the top of it ahead of the paver. Not so much for the concrete because you're pouring it in a form over the top, but rounded gravels are a cause of premature pavement failure. As far as concrete, we want to make sure we use the right concrete design for a particular project. On the left here, we're paving a roadway for a truck area. We use a concrete with a much higher finish strength. Made sure it had heavy-duty rebar, just like in the other example I showed you where it had poor drainage underneath. Made sure the rebar was put in the middle. We don't want to use like a sidewalk mix here because that's going to cause a premature failure. The photograph on the right is a school that we were brought in on. They're having this type of major spalling failure due to heavy salt usage. This was in a climate that they had a lot of freeze-thaw cycles, a lot of snow, and obviously they didn't want the kids to get hurt, so they used a lot of salt on their concretes. Well, their concretes were having premature failure because of it. By changing the mix design of the concrete, putting some additives in it, that stopped this premature failure. So the wrong mix design and the wrong concrete design in the wrong area can cause premature failure. Now, when it comes to asphalt, it's very similar to concrete. You have to use the right asphalt mix for the right job. A driveway mix has smaller stones, a little more sand. It gives it a nice tight appearance for the surface, plenty of strength for small cars and light trucks, and gives it that nice look that driveway owners are looking for. But that's not the type of mix we want to use on a commercial parking lot or a roadway. Those are much more high-tech mixes. Larger stones are used, the crushing of the stone, angular stones, and the modifiers put in the asphalt oil itself are very important to make sure that pavement lasts as designed. So an improper asphalt material can also cause a premature failure. Number 5, inadequate design. Usually when we talk about adequate design, it comes down to pavement thickness. This truck area on the left is concrete that we were brought in on. This is a concrete pavement that's between 5 and 8 years old. It's unlike the example I showed you with the poor base, it's cracked, but the slabs aren't rocking. They're not settling like where the slabs had collapsed under the poor drainage. In this case here, concrete was only spec'd at 6 inches deep. The cores actually showed that about half the cores were even less than 6 inches, so it wasn't even built to specification. But what's happening is the concrete was too thin to support the heavy loads of the trucks pounding over the top of it. And just like hitting a stone with a hammer in your driveway, that concrete was being hit by the tires and the loads, and that caused it to fracture and crack and fail prematurely. The photo on the right is another project. This was a concrete parking lot just for light cars and trucks, but it failed prematurely. Again, within 10 years, which is not, concretes are expected to last at least 20 years. Well, once the concrete was removed, it was found that there was no stone base underneath it. As you can see, it's just the native clays. It looks a little moist, so it wasn't real solid. So in this case, the design failure was not having a stone base underneath, because the stone base gave it that extra bit of strength. We didn't have to add much more concrete because it was just for cars and trucks, and thickening the concrete increases the cost. So digging out the clay, putting in a stone base, and replacing the concrete was a proper repair, and we should get 20-year life out of that concrete. Here's an example of inadequate design in asphalt. The photograph on the left was a project I was involved in where my first thought was that it had poor soils underneath and it was soft, and that's why the asphalt was cracked. But when we came in and removed the asphalt, we found that the stone base underneath was very hard, very hard. So the existing pavement was only 3 inches thick. It was like the concrete example I showed on the previous slide. The asphalt wasn't thick enough, so the heavy loads were breaking the asphalt against that hard stone base. So what we did was, after we removed the asphalt, we removed some more of that stone base down so that we could replace the asphalt with a thicker asphalt, and it's performing very well. The photograph on the right is an example of the same thing. This was a heavy truck exit at a factory. It was heavily alligatored. I expected it to be pretty wet underneath. Once we removed the asphalt, we found out that it was very hard. It wasn't yielding under the excavation truck. So all we did was remove a little extra stone and gave it a properly designed asphalt thickness to support the loads that were on that roadway. When I look at the design is kind of like an algebraic equation. The thickness of the asphalt pavement or the concrete pavement plus the thickness of the stone base must overcome deficiencies in the soil and the traffic load that it's going to carry. So in the design phase, how we try to take care of these root causes of failure is we do geotechnical exploration, we do borings, like it's shown on the slide on the left here. The borings show us how thick the existing asphalt is, how thick the existing stone is, and what the soil is made up of. Is it a sandy gravel? Is it a clay? Is there topsoil in there? And the other thing it tells us is moisture, how much water is underneath there. And some of the things we can use to offset that equation so that the pavement is stronger than the loads that are going to be on it and any deficiencies in the soil is we put in thicker stone or thicker asphalt or thicker concrete, but we can also reduce the thicknesses of those materials by using what's shown in the slide on the right. So the geotechnical fabric on the bottom separate the stone base from the soil so it doesn't intermix, so the stone stays solid and does what it's supposed to do. There's also a geogrid on top of this, which is basically a plastic grid that actually adds strength to the stone base. So those are some of the methods we can use to make sure that we don't have these premature failures and eliminate the root causes of those failures. And the last root cause of premature pavement failure is lack of construction observation and inspection. It doesn't matter how good a design you put together, the contractor doesn't follow that design or doesn't install that material properly, you're going to have premature failures. And here's a couple examples. On the left, this is a pavement at a shopping mall where they put the lower lift of asphalt in, decided to not put the surface on until the mall was built, and just run the construction trucks on the lower lift of asphalt. And that's fine. It's a great way to do it. But when the contractor came in to put the final surface on, they didn't get all the dirt and dust off that lower lift of asphalt. And there wasn't anybody there to let them know that they needed to clean it more properly. And so what happened was the upper lift of asphalt didn't adhere to the lower lift, and we had this sliding and shoving of the surface course. The slide on the right is a parking lot. I actually thought this was a gravel parking lot until I got out of my car and started looking at it more closely. This was an example of during construction, there wasn't any quality control for the asphalt. And so the material wasn't what was supposed to be installed. There was not enough oil or asphalt cement in the mix, so there wasn't glue to hold it together. So the asphalt started coming apart from the top down, became very raveled, and looked like this rough appearance of a gravel parking lot.
So Troy, a couple of questions for you on this slide. The photo on the left that you mentioned at the shopping center, any idea how old that pavement is that we're seeing the shoving in?
Less than a year. That surface course started failing within a year of being installed because they're just, as you can see, it's got a turn arrow there. As vehicles were slowing to make that turn, particularly buses, there was a bus route here, that braking just caused that upper layer to just slide right off the top of the lower layer of asphalt.
Okay, so in this case, if it happens within that first year, most likely it's under warranty. But could you touch on the kind of typical industry standards we see for warranties?
Yeah, unfortunately, the industry standard for pavements, asphalt and concrete is 1 year. It's pretty hard to put a pavement in that's going to fail within a year. So there's not a lot of recourse to have the contractor come back and repair these kind of things after 1 year. So that makes it extra important to make sure that you are inspecting the initial installation to make sure it's done properly, but also before that 1 year runs out, do a visual inspection of the new pavement and look for these telltale signs of premature failure.
But if I'm understanding you correctly, there could be times where we're not seeing the premature pavement failures till 2, 3, 4, 5 years. You know, one of the examples you showed was 10 years, but it should have been a 20 to 25 year concrete. So in those cases, there's not really much recourse to go back to the contractor for anything at that point in time.
No, not from a warranty standpoint. Obviously, you could probably get into litigation if you can prove that the contractor didn't follow the specifications and didn't do what they were supposed to do. But I think that can be very costly. And the chances of getting a contractor to come back and do anything after the warranty's up is pretty unlikely.
Sure. And that's where, as you mentioned in this slide, the construction oversight, inspection, and quality assurance is critical to the overall, to identifying this, any of these root causes ahead of time.
Yeah, it's definitely the weak link in making sure you get on a quality pavement. Some more slides on construction or lack of observation that causes premature failures. Slide on the left, it's pretty obvious here that part of it was installed properly and part of it was installed too thin. Well, you're obviously going to have a premature failure where that stone thickness isn't as thick. The contractor saved a lot of money because he didn't put all the stone in he had to, but this pavement is not going to last 15 to 20 years that it was probably designed to last. The slide on the right shows a example of a concrete pavement where during construction it was obviously overwatered. Either they put too much water in the cement truck before it was laid, or while it was being laid, the crew added more water to it because it was maybe getting away from them and setting up too quickly, so they needed to get the top to cream up. And it looks great when you water the top of it when you're done, but what happens is you lose all the strength on the surface of the concrete, and you get this scaling where the hard surface flakes off, causing this premature failure of the concrete. I think this concrete here was only 3 years old at the time I took this photograph. Many times less than what it should have lasted. Some of the advantages of, the construction observation, this project on the left, after it was excavated, it was found that there was a water spring underneath this pavement. Yes, the pavement could have been replaced, the stone could have been replaced, but the root cause of the failure wouldn't have been addressed, and it was easily addressed by installing an underdrain system. You can see there's a pipe there in the trench. That fabric will be wrapped over the top of it once it's filled with clear stone, and that pipe goes to a catch basin in the distance. So now that all that spring water is being caught by this pipe and drained out from that pavement system, and that pavement system will last as designed. The photograph on the right shows they had removed the asphalt, but there's obviously a poor soil here or an area of wet soil. And so many times you see contractors will just, knock those ruts down with a skid steer or even just rake them off and pave right over the top of it, and it'll look good for several years. But I guarantee that area is going to fail prematurely. So having inspection there, that would be dug out, stabilized, and then paved after we're assured that we have a good base. So another example of poor construction causing premature failures. So in conclusion, when you see a failure of your pavement, try to determine what's causing that failure. Look not only at the pavement, but around the outsides of the pavement. Look for those clues for subsurface water, clues of rutting or faulting concrete, and make sure that before you do a repair or full reconstruction that you address in your design phase these root causes of pavement failures.
Okay, so to summarize then, Troy, when a pavement is designed, installed, and maintained correctly, it should last up to 20 years. Most premature defects are caused by not addressing the root cause of the pavement failure during the design process or identifying them during construction. Benchmark is here to help you understand the root causes and identify what to look for before, during, and after your next pavement project. So what we'd like to offer to you for participating in today's webinar is if you have an interest in sending us a photo of a failed pavement that you have, specifically a pavement that you feel like might be a premature pavement failure, we would suggest that you send that photo over to us. You will receive an email as a follow-up to this webinar, and on that email there will be a spot where you can upload the photo. And what Benchmark is offering is that one of our consultants will contact you to schedule a visual meeting to review the pavement photo and discuss the premature pavement failures that you're seeing. We certainly can't see everything from a photo, but we really we'll work through as much of it with you as we can virtually, and give you the best experience and some basic advice and insight on maybe next steps and how to handle that pavement. Well, we appreciate your time today, and thank you for joining us for this webinar. And if you have any questions, please feel free to reach out to us. Our phone number is here on the screen. We hope you have a great day. Thank you.